this talk fits here because we've been hearing much about modulo space and the minimal model program. And although this is a very small example, it turned out to be not so innocent. So let me present to you what's M06 bar. This is going to be the sketch of the talk. We are going to start with some generalities on M0n, on monitoring spaces, on what or how does the minimal model program looks for a monitoring space, some examples, and then we are going to focus on the rational geometry of M06 bar. So let me remember to you that M0n, the open modulo space, are those systems of P1s, rational curves, with endpoints, and marked points up to isomorphism. And it has this celebrated compactification of the Link-Mumford, where it is added to the boundary stable curves. And these conditions here are what makes a curve stable. There should be nodal curves, and every component should be isomorphic to P1, should be rational. So the word singularities are no nodes. The arithmetic genus of the whole curves should be 0. And in every irreducible component, there should be 3 special points, which should be either a node or mark points. And these conditions make, this third condition ensures that you don't have too many isomorphisms of the curve. And this is the modulo space M0n bar, and it's a smooth, compact, projective algebraic variety. So let me give you a cartoon of what's in the boundary. So we have added to the boundary divisors, and these are the nodal curves. So this is this is how they look. So the general point in the boundary looks like 2 components, 1 node, and then the mark points distributed in each of the components. So the boundary is parameterized by partitions. How many ways can you divide this set? And in such a way that every side of the partition has at least 2 elements. This ensures that you don't have unstable things here. And the whole boundary is stratified by topological type. So we have codimension K strata, which is the classes of things, of curves that have exactly K nodes. So you have K nodes, and it's going to form a codimension K thing, stratum, the modulo space. So this is how it looks at generic point in the divisor delta I with I equals 1, 2 in M06 bar. This is a curve in M0. This strata forms a curve in the boundary of M06 bar as well. So it has 2 nodes and the points distributed in each of the components. So we have, for M0n bar, this very, very nice and useful description of Kapranov's. In fact, Kapranov's description is even larger, giving it as a child quotient of Gersmanians. But this one is the one I'll be using today. M0n bar is isomorphic to a blow-up of P to the Pn minus 3 along linear points. So, linear spaces. So you blow up first n minus 1 unique points, and then you blow up along lines through these points, and then along planes, if you can, through these points, until the codimension is 2 of these spaces, of these linear spaces. This blow-up is order, it's important, the order, but you can do it in this order, and this is enough. And so it shows that that M0n bar is really a simple object. It's just blow-up of Pn minus 3. So we have as an example that M05 bar is the blow-up of 4 points in P2. That means that M05 bar is just the Del Pezzo surface X4. M06 bar, in the other hand, is the blow-up of P3 along 5 points, 5 generic points, and then along 10 lines passing through each of pair of points. In consequence, the Picard group is very simple. It's just a free abelian group. It's isomorphic to Z to the R, where the generators are the hyperplane class and then the exceptional divisors arising from the blow-up. So for M05 bar, the Picard group is isomorphic to Z to the 5, and for M06 bar, the Picard group is isomorphic to Z to the 16. The 5 exceptional divisors arising from the blowing up the points, and then the 10 from blowing up the lines. Okay, that's what I need to know about M0n bar for the moment, and then let me move to Mori dream spaces. So what's a Mori dream spaces? In this paper of Mori dream spaces and GIT from Juan Kills, I think, Juan Kill, I think that's the title, not the authors. They define that a smooth projective variety is a Mori dream space if the following happens. The Picard group should be the same as the Néron-Severi group. It also should happen that the Neff cone of the variety should be a rational polyhedral cone. And then they should have only finally many small birational modifications, Q-factorial birational modifications. And that basically implies that you can carry on the minimal model program on your variety X, that you can perform the flips that is needed. So in this graph presentation of the minimal model program, you're going to find an endpoint. You're going to find a minimal model. And then they went on to prove that you can have you will have a Mori dream space if and only if the Cox ring is finally generated. And so, for those of you that may not know what's the Cox ring, you basically choose a basis for the Picard group of your variety, and you consider for every A in Z to the R, so the Picard group has rank R, you consider the sections of this divisor, D1, D1, AR, DR, and then you make the sum, the direct sum of all of them. And this monster, it's a huge thing, has a structure of a ring, and it's called the Cox ring of your variety. If this thing is finally generated, then you have a Mori dream space. And further on, they prove that if you have a Mori dream space and this thing is finally generated, then you can recover your variety as a GIT quotient of an affine variety by a torus action. And it's really, really convenient. So you have the Cox ring, which admits a presentation of as a C algebra, a finally generated C algebra. It's a Picard graded ring. The ideal of relations here is Picard homogeneous. And then you can get X as the GIT quotient of the variety associated to this ideal mod an ample class. By the action of G, and the GIT quotient is related to this ample class. So who is G? G is the group of morphisms from the Picard group to C star, and this is a torus. So if your space is a monitoring space, you have a very, very simple presentation of it. And then the minimal model program for a monitoring space is really just to understand how to do the minimal, how to do the variation of these GIT quotients here. And variation of GIT quotients here relates to variation of GIT quotient of a affine space. So it's BGIT in the toric variety. And this is a purely combinatorial game. For a toric variety, we have that the Cox ring is only a polynomial ring. And in fact, if you have the quotient, the GIT quotient of a affine space by a torus, this is going to be a toric variety. If whenever you have a toric variety, you can recover it as the quotient, the GIT quotient of a affine space. So moreover, there is a one-to-one correspondence between closest subvarieties here and ideals of the coordinate ring of the affine space. Ideas, not any ideas, but radical homogeneous ideals containing this ideal alpha determined by the ample class. And I will tell you later at least I will mention how do you get this ample class ideal. Okay, so how does it look BGIT for a torus action? I said to you this is a purely combinatorial game. And what happens here is that if you have C star acting on a affine space with these weights, you can write the weights in a matrix A, and you can compute the Gale dual for the Gale dual B for A. And what's this? This is a matrix whose transpose has the kernel of this matrix here, this set kernel, the kernel over set of this matrix here. So this is the definition of the Gale dual. So let me just write not to lose you. B is Gale dual for A, and A has entries in set if B transpose times A equals 0. And this is an integer matrix as well. So you have the matrix B there, and you can think of the columns of the matrix B as points in set to the n minus the rank of this matrix A. So in some set to the S if you want. And you can think of them as giving you a configuration of vectors. So perhaps you have these vectors there. One more vector here. So these are the vectors here that you get from the columns of the matrix B. So what is surprising here, well, at least it's surprising for me, is that the different GIT quotients that you can get for the torus action are in correspondence with the regular subdivisions you can get to this vector configuration. So what's a regular subdivision? It's a subdivision of the cone defined by this. So you consider positive whole of V1 up to Vn. And you want to subdivide, but not in any way. You subdivide in the following way. You leave B1, you choose W and set to the n sufficiently large, or positive at least, B1. And so you make the point B1 with the entry W1 up to B n with the entry Wn. And this is going to be a vector configuration in set to the S plus 1. So you lift it and take the positive hull of it, and then project the lower faces of this lifting to the original configuration here. And in that way, you're going to get a regular subdivision. So the GIT quotients are in correspondence to those subdivisions. But how do you parameterize those subdivisions? Well, you define, so we take set W in fact in Rn, and you make W1 to be the same as W2 if they define the same subdivision in this way. So in R to the n, you have a fan structure which parameterizes all the possible subdivisions. This is in R to the n. It turns out that this fan has a linearity space, and if you mod out by the linearity space, you get a smaller fan, but this time in set to the R. And this is called the secondary fan, the polyhedral fan whose cons parameterizes the regular subdivisions of the vector configuration B. The support of the secondary fan happens to be precisely the positive hull of these vectors. And then if you take an element, a character chi, in the positive hull of these vectors, this character will correspond, because this is the support of the secondary fan, this character will give you a subdivision of this vector configuration. So you will have, so chi will give you a subdivision which is going to be a simplicial complex of the form I1, IR, etc., telling you how to divide. So if, for example, if this is my vector configuration 1, 2, 3, 4, so for this subdivision I will get 1, 2, 3, and then 2, 3, 4. This is going to give this subdivision of this vector configuration. So it's going to be a simplicial complex. And if you have a simplicial complex, you can associate a monomial ideal, the Alexander dual ideal. And this ideal is going to be in n variables, as many as the elements on your vector configuration. So you have an ideal here, and it happens that the zero locus of this ideal gives you the unstable locus for the action. So whenever you have a point in the positive pool of the weights, you will have a definition of the unstable locus for the action associated to that point. And two characters are going to be in the same secondary. So this is a fan. It's a collection of cones. And they're going to be in the relative interior of the same cone if and only if they define the same semi-stable locus, or if you want the same unstable locus. So really, the GIT quotients for this action are given, or at least the chamber decomposition for this action, the GIT chamber decomposition, is given by the secondary fan. So nothing of algebraic geometry here except perhaps the Alexander dual ideal, but it's surprising that it's just pure combinatorics. So what happens for a Mori dream space? Well, if you have a Mori dream space, you can perform GIT on the ambient space. So remember, Mori dream space means you have the presentation of the Cox ring, and you have an ideal, and you can recover the variety here. So if you have all this information, you can perform variation of GIT on the action of G on the affine space, the ambient affine space. So you compute only the secondary fan for the action, and then you determine the semi-stable locus by checking if you add the ideal of your variety to the unstable locus and take the radical, you check what's the zero locus of this ideal, and this is going to give you the unstable locus inside V. And then the Mori chamber for X is going to be the gluing of secondary cones. When two cones give the same radical, they will give you the same unstable locus, so they will give you the same GIT chamber for V. And then it's going to give you the same Mori chamber for X. So really, to get a Mori chamber decomposition for X is only to get the GIT chamber decomposition for B. Sounds, yep?
When you say Mori chamber and secondary cones, it means that in the secondary subdivision there are cones which can glue together and gives the same minimal model?
Yes, so I'm computing the, I'm saying that you should compute first the secondary fan for the G action on the affine space. So if you want the variation of GIT chamber decomposition for that action, you get the secondary fan. But this is not, and it's going to be the composition of the effective cone of X. But it's not going to be the decomposition as Mori chambers. It's not going to be the composition as Mori chambers because the Mori chambers of this variety are going to be the GIT chambers of this variety, of the V.
If you have two cones which belong to two cones of the secondary subdivision which belongs to the same Mori chamber, it means that going from one cone to the other, you perform a rational transformation?
No, not for your variety. No, what it's going to mean is that those two cones, so you're going to have chi1 and chi2, and it will happen, the chi1 and chi2 define, when you make this ideal sum, so you sum this, the Alexander-Dural ideal related to chi1, and then the Alexander-Dural ideal related to chi2, and you perform the sum and take the radical, they will give you the same thing. So they will define the same unstable locus for V. And then if they have the same stable locus, unstable locus, then when you take the quotient, they will give you exactly the same quotient. So as a model for X, they will represent the same model. So if they belong to two different, I glue them because they represent the same Mori chamber. For.
Okay, but crossing the wall between the two cones in the secondary fan does not give you some...
Not necessarily, unless they represent actually two. They do for the affine space quotient, but not for the variety X. So we get the Mori chambers by gluing secondary cones in secondary chambers in the G action of affine space. So why is this relevant? Well, here are some good news and bad news. The first good news is that for n equals less or equal than 6, M0n bar is a Mori dream space. But for for n greater than 134, and in fact, I think it's 13 the correct number at the moment, M0n bar is not a Mori dream space. It's no longer a Mori dream space. So we have this window here between 7 and 12 where it may be a Mori dream space, but nonetheless we have two fine examples where we can try this sort of algorithm I provided here for computing Mori chambers of the moduli space. So let me show you this example. For M05, this is, I've said this is a Del Peso surface, and it was established by Batirev and Popov that it's a Mori dream space. They computed the generating sections for the Cox ring, and they gave relations as well. So the presentation of the Cox ring of the M05 bar is this polynomial ring in 10 variables mod this ideal. So I've called these variables xij, and it comes from the fact that you have the boundary on M05, and the boundary is parameterized by these pairs, xij, because the only way you can have a partition I complement of 1 up to 5 is that you have a partition of size of 2 elements with at least 2 elements in each of the sides. The only way you can have this is that you have at least 2 elements. So all of them are parameterized by the size 2 side of the partition. So these xi are the sections over the boundary divisors. And this ideal is the ideal generated by the Flocker relations. So if you want, this is kind of isomorphic to the homogeneous coordinate ring of the Grassmannian. So we have the presentation of the Cox ring. We have a basis, a suitable basis, so you can make a suitable change of basis so that the degree of these divisors is EI plus EJ in Z to the 5. We know an ample class, so we have everything we need to perform the program I described before. So we do this using a computer, and we get that the effective cone of M05 decomposes into 76 Mori chambers. The F cone is the positive hull in the choice of bases I made before. This is the positive hull of these columns here. So you get 10 generators for the F cone. And up to symmetry, there are really only 6 Mori chambers, and the one corresponding to the F cone, and then this. The good news is that all the Mori chambers here are the known weighted moduli spaces from Hassett. So he described these weighted moduli spaces. And each of the symmetry classes tells you which points can come together in his description. So these are all known models, and it worked perfectly fine. So now we move on to M06 bar, and we have now 25 boundary divisors plus 15 extra divisors, and these 15 extra divisors, these 40 divisors in total, they span the effective cone. So the effective cone is polyhedral and generated by this. And we have this theorem of Castravet that says that the sections over these divisors generate the Cox ring. So the Cox ring of M06 bar admits this presentation, the quotient of the polynomial ring in 40 variables by an ideal. This is promising. If you knew what the ideal is, well, we knew what the ideal is. So we have all these variables. And Xi, you can choose if the partition has 2 elements. It's 2 and 4 elements, or 3 and 3 elements. And that's what's represented by these variables. And these are the relations among these sections. Let me tell you here, this looks pretty much like the Plocker relations. IJKL, IK minus IKJL minus, plus IL JK, save that there appears these elements here, these variables here, and they make this homogeneous in the Picard grading. So we make the computations, we conclude that there are 225 relations. So sounds good. We now can compute the Mori chambers for M06 bar. We have a presentation, we have the ideal, 40 variables, 225 polynomials here. We know the generators. We even know an ample class. So I said before, we only need to perform the variation of GIT for the affine space A to the 40. And that means computing the secondary fan of a Gale dual of A, where A is the matrix whose columns are the generators of the effective cone, 40 columns in Z to the 16. Doesn't sound that bad. B may look impressive, but it's a 24 times 40 matrix. You can make a change of basis and make this matrix the identity matrix of rank 15, 0 matrix here. This is a 9 times 25 matrix. So doesn't look that bad. We need to compute the secondary fan of this. And of course, we need to compute these radical ideals. Yeah? Oh, sorry. Yeah, yeah. So we will do it when my son gets to his PhD, because the computer is just simply not able to compute the secondary fan. But we don't get into despair, because we have this proposition. We don't need the whole effective cone. we can do it with only the boundary cone. So the GIT chamber decomposition of the cone spanned by the boundary is the only thing that matters. And we can get the Mori chamber decomposition of this thing from the secondary fan of the matrix B prime we have here. Okay, so this is these two slides. We want the flips of M06, right? And they are important because M06 is three-dimensional, and flips finish for three-folds, right? So we should be able to find a flip for M06. We should be able to compute them. And it didn't happen so straight away. So we have a hand on the F cone of M06 because we have a hand on the Mori cone of M06. So we compute the Mori cone, we compute the effective curves, and we compute using a small computer. You can compute the dual because the dual is with the intersection product. And it happens that the Mori cone has 65 extremal rays, and the F cone has only 3,180 rays. And up to symmetry, really, there are only 26 rays. So we need to concentrate on only 26 rays. Up to symmetry, there are only 2 extremal rays. So if the facets of the F cone are in correspondence with extremal rays of the Mori cone, and the flips corresponds to the GIT wall crossings in the F cone, then we need to compute only such 2 of them up to symmetry. So the work in progress is to find, once we know the F cone, and we know the equations for the curves defining the facet of the cones. So we want to cross the other side of the wall and compute the ring associated to a character in the other side of the wall. And of course, to explicitly say what this variety is going to be and whether it is a minimal model or not. I perform more wall crossings. And the other thing that is being doing is to find the corresponding maps defined by the rays of the F cone. So this is what I've done.